Welcome to the presentation. A gray level image is a type of image in which each pixel is a shade of gray ranging from black to white. In a normal grayscale image, each picture has values between 0 and 255, where 0 corresponds to black and 255 corresponds to white. In between those values, from 0 to 255, are varying shades of gray, where values close to 0 are darker and values close to 255 are lighter. We will assume that the image is of size m by n. A histogram is an array of counters, and the number of counters is equal to the number of gray levels in the image. To construct the histogram, we need to look over all pixels in the image, and when encountering a pixel with gray level k, we increment the counter. So that will be the histogram obtained by counting all these possible gray level values in the image. Notice how for this particular range there are a good number of pixels in the image, but nevertheless we don't have blacks, which will correspond to values close to 0, or whites with values that corresponds to 255. If we normalize the image, what we can obtain is an approximation of the probability density function associated with the original image, and we're going to denote it P of RK. What we want is pixels like that, as highlighted in yellow, that are not completely black. For example, let's say that that pixel has a pixel intensity of 75. What we would like is to change it to 0. So the output of that transformation, the pixel, I will be naming it S, where R will be the input of a mathematical function that hopefully will make that change. Pixels that are brighter, such as that one, with value equals to 155, I would like to convert it into a complete white, 55, so that I can actually in this image obtain all the diversity of gray level values, and that will give me an image, hopefully with a histogram like that, which is completely uniform. So such a uniform histogram in a final image will give me a lot of contrast, because I will see values that are dark all the way to light. So I need to find that mathematical function S equal to T of R, where I'm going to change the intensity of the pixels R and convert them into S, so that I can obtain an image like the one I'm showing you on the right, where you can see that image has all the possibilities from black to whites, and usually we see it as an enhanced contrast image. In order to find the transformation function that we're looking for, we know that we have the original PDF of the original low contrast image, PR, and that transformation function will have the following restrictions: that to be continuous and differentiable over the range of values of interest, so that we can go from the PDF on the left, the red one, to the uniform that we want. Then the PDF of the transform map variable S can be obtained as that expression. The easiest case for transformations of continuous random variables is the case of a one-to-one, by starting with the cumulative distribution of S equal to T of R in terms of the cumulative distribution of P of R. Algebra of random variables offers us the expression just presented. By using the derivative of R with respect to S and substituting, we can obtain the uniform distribution, as we can see here. Note how the PDF of S is uniform with probabilities of 1 over L minus 1 equally. The solution then, S equal to TR, just becomes a lookup table where for an input value R of the original pixel, intensity will get transformed to S to obtain the uniform distribution. For example, for a pixel of value R equals to 50, in the lookup table we see that the output will correspond to S equals to 0. At the same time, a pixel lighter than that, let's say value 125, will be mapped to S equals to 180. Processing all the pixels like that yields the histogram we're showing here. If we zoom in the transformation function, we can see that a couple of values yield the same result on the transform image. We want a histogram that is complete uniform instead of the one in blue where we can see gaps and the bars are not exactly at the same height. The histogram denoted H will have the sum equals to mn in order for us to normalize it. In order to achieve this, we will refer to a technique named exact histogram specification. The steps involved in these techniques: order the image pixels according to a predefined criterion, split the ordered pixels into L groups such that group J has exactly H of J pixels, and assign intensity value J to all the pixels in group J. As it can be seen, the histogram will have equal probabilities for every gray level value. Recall once again how different pixels will land with the same gray level value at the output, creating those gaps in the histogram and the non-uniformity of it. Going back to the method, imagine that the image can be transformed such that every pixel will have a different gray level value. Notice how the pixels, color yellow, have intensities that are very similar in this region as well as this other region. Every pixel will have a unique gray level value starting from 1 all the way to mn. Thus, none of them will share the same intensity value. Exact histogram equalization can be achieved if we order all those pixels 1 to mn in such a way to consider not only their gray level values but their proximity. Let us consider discrete images having L gray levels of gray. We look for additional information in the local neighborhood of each pixel to eliminate the ties. Define first a general model for pixel ordering by using an operator defined on the set of discrete images. In order to induce such an ordering, the pixel neighborhood is taken into account. By using a vector operator, the problem is transformed from a scalar image to a k-dimensional space by associating a vector to each pixel, and then by lexicographically ordering the vectors, the same order is induced among the image pixels. The vector operator can be seen as a filter bank. Thus, we will consider a family of neighborhoods around each pixel. Each VI extracts some local information about gray levels around the current pixel. The inclusion among the filter supports is intended to somehow order the amount of information extracted by each filter. Thus, when I is small, the information extracted is strongly connected to the current pixel. As index I increases, support increases as well, and the weight of the current pixel decreases in the filter response. This is a reason for ranking pixels using the lexicographic order, starting with the first index. This ordering allows us to have pixel intensities from 1 to mn. Then the first block of size mn divided by 256 will be assigned gray level 0. Next block will be assigned gray level 1, consecutively until we have 256 blocks of equal size. Using this technique, we go from a histogram that is not necessarily uniform to the one showing you next. Let's call both results A and B and see how the pixel magnitudes differ in all the places where there is a difference between both results. The image shows how in the white areas there is no differences between the magnitude of the pixels of both results. And we can see how the maximum intensity differences is only 5. Links to the references are provided below. Thank you.